Okay, we have, everybody, we have reached our final section in Calculus 2, section H.2, areas and lengths in polar coordinates. We will focus on areas. So just like we want to find areas under a function y equals f of x from two limits, a to b, we also want to be able to find areas under polar curves from two limits. Okay, so the situation we're talking about is a situation like this in figure 2. So in figure 2, you see there how you have a polar graph, r equals f of theta, and you have a starting angle, theta equals a, and an ending angle, theta equals b. Okay, you have a starting and an ending angle, and between those angles, there is shaded blue area underneath the polar graph, r equals f of theta. So how do we find that area? How do we can't treat this exactly the same as, well, it's going to involve a Riemann sum, but we got to do things a little bit differently. So what we're going to do is what you see in figure 3. We're going to take that area of the region and break it up into different sectors of circles. And so you see there all the little divisions. Every division is a sector of a circle, okay, where the radius is equal to the function f of theta. That's that dashed line in figure 3. And the sector of the circle starts at theta, at point theta I minus 1, and then the sector ends at a point theta I. So if we could find an expression for the area of each of the sectors of those sectors, and then take the limit as n goes to infinity. In other words, we'd have a bunch of circle sectors. That the sum of those areas would equal the area you see in figure 2. That's the idea. So the area of a sector of a circle is equal to 1/2 times r squared times theta. Let me deactivate my email here. I don't want any distractions. Yeah, 1/2 r squared theta. So how many have maybe seen that formula in the past? Maybe when they were in middle school or high school, the area for a sector. Okay, Jonathan recalls that. You know, if I go to the whiteboard and I just write that formula down, area equals 1/2 times r squared times theta. Well, let's think about a circle. A circle, okay, I want to be a little bit careful here. Let me see, one moment. So the circle has area what? What's the area of a circle? You remember? You should know that. That's right, OPME. Very good. Very good. Pi times r squared. Well, a circle, so this here is this formula above is the area of a sector of a circle, right? A full circle has an area of pi r squared, but a full circle, it has angle 2 pi, because the circle, to complete the circle, right, you start here and you got to go 360 degrees to start to finish the circle. So the circle, the theta, is equal to 2 pi. Well, for the area of a circle, then, if we use this formula here, it's going to be 1/2 times r squared times 2 pi. And so that's going to get you pi r squared. So, you know, this formula, a equals 1/2 r squared theta, might seem a little bit strange, but it certainly works for, you know, the area of a circle. And, you know, sometimes I show students that so that it helps them feel a little more comfortable. Now, what are we going to do with this? What are we going to do with this? All right, well, let's go back to the ebook. So we have this area of the sector of a circle. And remember that to approximate the area in figure 2, we need to inscribe a bunch of sectors, sectors of circles of different radii, and add up those areas. Every piece of area, okay, every little piece of area, delta A, okay, is equal to 1/2 times the radius f of theta squared, and theta sub I is, well, the delta sub AI, which is the piece of area, the ith piece of area, is equal to 1/2 times the radius squared times delta theta. Delta theta is the difference between the starting and ending angle of the ith circle sector, and that's always going to be this. We'll make that the same. And then we define the radius of that sector by picking some theta I star value that's located between your beginning and ending angles for that sector. So you can see that in figure 3. Quite beautiful, actually. So, okay, if we were to then approximate the total area under the polar curve, we would have the summation of 1/2 f of theta I squared times delta theta. But what are we going to do to get the exact area? We're going to take the limit as n goes to infinity. And so this is going to give us then the formula for the area of a polar region. The formula is the integral from a to b of 1/2 times f of theta squared. That's the formula. And since the radius is equal to f of theta, we often express that formula as just the integral from a to b of 1/2 times r squared. And we're integrating with respect to theta, because a and b are, for whatever polar region you're graphing, a and b are your starting and ending angles for that region. Are there any questions so far? All right. Well, let's take a look. Let's take a look here at an example. Let's go ahead and take a look at an example. And let me just see here, class. Hold on. Yeah, let's do this example. And then we'll take a break after this example, but let's get this one in. Okay, let me give you a moment to copy this example down. Okay, so we want to find here, we want to find the area of the right half of the region enclosed by this polar curve, r equals 4 plus 3 times the sine of theta. What would you recommend the first thing we should do is for this problem? What do you think the first thing we should do is to start this problem that will be helpful for us? Let's say this were on the final exam. What would be helpful to do? How many of you would like to know what this region looks like? Okay, so that's right. Victoria, Jonathan, that's right. We got to do a graph. Now, if we graph this in Desmos, I'll tell you what, I'll go to Desmos and graph it. All right, let me just see here. Hold on. Let me go to Desmos. Okay, so we're graphing r equals 4 plus 3 times the sine of theta. Obviously, I got a typo there, don't I? That's better. Let me zoom in a little bit. Whoop, nope, zoom out, zoom out. Move this down a little bit, maybe. There we go. That's a pretty good picture, right? And what we want is, we want this region, which we call a cardioid because it looks like a heart, cardioid. We want the right half of the region. So if we were to take this region, which is symmetric about the y-axis, and cut it down the y-axis, we want the area to the right. Are there any questions on graphing the polar graph? Okay. Well, so here's our picture. Here's our picture. So I can put, maybe I'll label one polar coordinate here, just hold on. This point here has a radius of 7, and theta is pi over 2. Because you're looking in the direction of 90 degrees and you're moving out 7 units, and that gets you at that point. So, all right, area is equal to the integral from a to b of 1/2, hold on, 1/2 r squared d theta, right? What are the starting and ending angles for this shaded area? Well, we could think of the shaded area as starting here and ending here, right? So let me just see here. Hold on. One moment. This point here, okay, is going to have polar coordinates 1, negative pi over 2. That's theta. Because if you look downward from the origin, if you look downward, you're looking in the direction of negative 90 degrees. If you say, okay, r equals 4 plus 3 times the sine of negative pi over 2, that is going to equal, well, the sine of negative 90 degrees is negative 1, right? So this is going to be 4 plus 3 times negative 1, and that's 1. So you start here, and you end up at 7 pi over 2. That's the ending point of your pole. That's the ending polar coordinate. If you say, okay, r equals 4 plus 3 times the sine of pi over 2, that equals 4 plus 3 4 plus 3 times 1, and that gives you the 7. So I'm just trying to provide some details about, how am I getting those polar coordinates? How am I getting them? And also what you can do, class, to sort of confirm that graph, I actually just sort of thought of this. Let me just show you in Desmos. I can go into Desmos here. And you see what I can do is here, to sort of confirm that, I can go into Desmos and I can put in negative pi divided by 2 for the beginning angle, and then pi divided by 2 for the ending angle. And you see, it gives me the right half of the graph. How many think that's pretty cool? That you can kind of use Desmos to confirm things. Victoria likes it, Avery likes it, Mark likes it, and these things do take time, and that's why, again, the final exam, I'm giving you even an extra half hour for part 1 and for part 2. So you can do things like this, you can do things like this and be able to, I mean, nobody's ever completely relaxed, right, on a final exam, but if you have time, just have the time, hopefully you need, you'll be more relaxed and do well. Okay, so that being said, let's go back to the problem at hand. Okay, so now we utilize the formula to locate the area. Well, to find the area. There it is. That's the formula. And of course, 4 plus 3 times the sine of theta. Okay, if I can expand that. Okay, so the 1/2 I bring out front here. I always bring constants out front. And 4 plus 3 sine theta is 4 plus 3 times the sine of theta times 4 plus 3 times the sine of theta. And you're going to FOIL that. You're going to FOIL that. And when you FOIL that, you're going to get 16 plus 24 sine theta plus 9 sine squared of theta. Well, are there any questions up to here? If I do it in the whiteboard, maybe I'll just do it real quick in the whiteboard just so you can see it. Hold on here. So 4 plus 3 times the sine of theta times 4 plus 3 times the sine of theta. Okay, that's 4 times 4 plus 2 times 4 times 3 times the sine of theta plus 3 times the sine of theta times itself. Well, that just equals 16 plus 24. 2 times 4 times 3 is 24. Sine of theta plus 9 sine squared of theta. Any questions on that? Okay, let's get back to the problem then. So this gets us then here, and I'm going to go ahead and write that sum, the integral of the sum, as the sum of the integrals. And with, if we use trigonometry, we can help make our computations a little easier. So, like the integral here of the sine from negative pi over 2 to pi over 2, well, that just equals 0. Here's a graph of the sine function. You have negative area and positive area. You're going from negative pi over 2 to pi over 2. But the negative area and the positive area cancel each other out. And so that integral equals 0. Okay. And then I note that the sine squared of theta, right, sine squared of theta is the same as sine of theta squared. And so if I graph that, you'll see that this graph is symmetric about the y-axis. I don't have enough, I'll say about y-axis, the graph is symmetric. And so, everything's good here. Let me just, yeah, so this is symmetric. You have to forgive me, I don't want to rush, but I do want you to get your break here. This graph is symmetric about the y-axis, so this positive area and this positive area are the same. Okay, in other words, this area here and this area here are equal. So I could write this integral here I could express it as 2 times the integral from 0 to pi over 2. Hold on. I can do better. Yeah. 2. Yeah. So I can express the integral from negative pi over 2 to pi over 2 of sine squared theta. I could express that as 2 times the integral from 0 to pi over 2 of sine squared theta, right? They are equal. And 0 is always a nice limit to have in an integral. It makes it easy to work with. Okay, so, sometimes before you just kind of rush to do the integration, see if you can use, maybe some kind of symmetry of the graph to help you. And so now my area can be expressed as you see here. And the sine squared root of a theta, well, there's an identity for the sine squared root of a theta. Sine squared root of a theta equals 1/2 times 1 minus cosine of 2 theta. How many we call that in trigonometry? How many we call that identity? Yonatan remembers it. And naturally you'll have access to those identities on the exam because you have access to the appendix C, right? And so now it's just a matter of doing some integration, getting your antiderivatives, plugging in pi over 2 and 0 carefully, and getting to the final answer, which is 41 pi over 4. And that's the answer WebAssign's going to want, by the way. It wants simplified radical form answers, not decimals. Let me give you a moment to copy it, and let's see if there are any questions. So, you just have to be careful when you compute things. The pi here comes from 2 times pi over 2, right? And 0 is just because you have 2 times 0. I'm talking, when you do the 2 theta part. I mean, is there anything difficult about this? Do you have any questions? After our break, we'll look at another example. We're not done with section H.2. We're not done, and we're going to do another example after the break. And on Wednesday too, I think we'll look at yet another example. But I think this is very helpful. All right. Well, if there are no questions, I will stop the recording then. Last chance if there are any questions. at least for now, right? Clea, yes, yes,
Actually, I have a question related to the final exam, if that's okay.
sure, sure.
Um, so I saw the date is like 19th of December. So is that the date that we have to take the exam plus the remediations?
No, well, so the final exam will be ready for you. Um, hold on. I'm going to answer that question. Let me go ahead and stop the recording here. Good question. Um, well, no, I'll just mention it. So the final exam will be ready for you on Monday, December 13th at noon. And you can take the final exam. You can do parts 1 and 2 early if you want or later if you want. But the deadline to complete parts 1 and 2 would be Sunday, December 19th at 11:30. That would be when you'd have to complete the final if you were to take like the whole week. Does that make sense?
Yes. And then for remediations?
Remediations, the deadline to complete those would be Tuesday, December 21st at, I'm looking at about 3 o'clock, like well, sorry, like, I'll have to think about that. I'll have to
Oh,
think
okay.
about that, but it would be Tuesday afternoon.
Oh, okay.
Okay.
Professor, is it been decided what topics that we already done will be
On
covered?
Wednesday, I'll have that. On Wednesday, I will have that information for you. I'm working that out. I
Oh,
promise,
okay.
Clay, I'll have that to you on Wednesday.
Okay.
I
Thank
know,
you.
no problem. Excellent. All right, and let me just see here. Um, okay, all right, let me stop the recording here. Excellent. Let's take a break.